on Wednesday, if you can get through these 4 problems, even make, good headway, you really have seen just about almost everything that could be thrown at you in terms of an application for Piecewise. These are really what we call rich problems. They really force you to think about the situation and try to apply what you've learned. So the fact that you may be having a little bit of problem like graphing some of these, it's to be expected at this point in time. I would be really shocked if there was anybody that came in here and zipped through these problems with no questions or no errors. I mean, and it's by making those errors and rethinking them that you get the clarity. Okay, so it's fine. However, I have 30. They're a little bent because the guy that was sitting right there in my first class had his legs crossed and he had a wasp, like this major wasp on his leg. And my 16-year-old came over, took my stuff, whack, killed the thing. But they're a little wrinkled, but I don't think the guts are anywhere. So anyway, so this is the answer key. This is the answer key. I think it was a wasp. It could have been a hornet. I don't know. Just some creepy crawly thing that looked pretty scary. All right. So you can come up and get one of these or see me. I just want to see how far you've progressed anytime between now and whenever you finish. All right. So that's your little motivation to hopefully see that. All right. Today, quiz 4, remember, is on Monday. And if you are one of these types that really feel like you don't want to think about time pressure, just come in here early. You know where I'll be. I'll be in the studio. So just come get me and I'll get you set up. So did you get my email about homework 10? Okay. And if you didn't, read your GCC email. Project 2 is due when? A week from Monday. And what's the date on Monday?
Wait, isn't it Columbus Day a week from Monday?
So when is it due? It's the 16th. So what day is the 16th? Wednesday. So it's due 10. Oh yeah, I got a dentist appointment the next day. Ouch. So it's due 10/16. So it's a while away, but don't leave it to the last minute. You can start the beginning of your project, as I mentioned. When we get to linear regression and something called correlation coefficient, you've got to wait till Wednesday before we cover that. But you can get a good start on this. 3:07s today, start time for the Red Sox. Go Red Sox. No, the Phillies got creamed last night, 9-1. Well, I'll root for Phillies. I've been to the... Oh, yeah. Well, I've been to a Phillies game. It's a wild place. That was Victorine. Oh no, who was it? Who was the guy? Oh, Bobby Abreu was out in right field. I had this like young kid behind me. I got to shut this off. Anyway, today we're going to talk about slopes of lines. Now, and equations for lines, because Ian got me distracted thinking about the Phillies. That's what it was. Okay. So I hope the Red Sox do better than the Phillies today. Okay. Plus, who are they playing? They're playing St. Louis, right? Oh, does anybody know if the Dodgers won last night? I want them to lose so bad. Does anybody know? Okay. I'll have to look it up. You can look it up, Ian. All right. So I'm going to tell you folks, today I'm going to go fast. And the reason I'm going to go fast is I'm assuming this is all review. Okay? This is all review. So, has anybody in here never seen the equation for a straight line or heard of the idea of slope? Anybody not heard of that or seen it ever before? Can I throw something at you now? Okay. So you see what I mean? You've all heard this lecture and seen this stuff. So I'm going to go fast because I really want you to start working on your exercise. If at any point you don't get something I'm doing, just tell me. Say, wait a minute, Linda, slow down, or that spot's a little fuzzy for me still, even though I've seen this before. It's been a while, okay? So I'm just going to go, I'm going to use you as my guide for how fast I go. And if you're all steaming along, I'm even going to go faster. How's that? Would it be possible? Then you'd have to like use some kind of special recorder. Yes, Ian? Oh, shoot. Okay. All right. Well, I was almost happy. All right. So slope, the definition of slope, you've seen it, you've probably done it. Slope measures the steepness of a line. Okay? And all of these versions are how maybe some way that you've remembered it. A lot of people who don't like notation like this little mnemonic device of rise divided by run. You say rise over run. Okay? So that rise represents the change in the vertical direction and run is the change in the horizontal. Another way you can write it, this is like the fourth way I've seen it, is to say change in y and change in x. They use the Greek letter delta. This is the Greek letter delta, and it means it's just a triangle. That's how they write it. It's similar to our D, I guess. You could almost see that. Change in, and that's what it means. Change in y, change in x. Okay? So let's calculate a few slopes, and then we'll be on our way. So here's the first problem. We have -3, 4. So I go to the left 3, up 4, -4, -2. Okay, and I want to connect those two lines before I start to graph it. Does anybody see what I did with the, oh, there it is, the ruler. So you connect those two lines before you even calculate the slope because you want to at least know what the sign of your slope is. Is it going to be positive or negative? So the way you determine that is you move left to right. And as you move to the right, as x increases, if y increases as well, then you have a positive slope. Or as you move down the line, if you go down and to the left, that's also a positive slope. So we know our slope once we do our calculation of the change in the vertical distance over the change in the x, or the rise over the run, however you remember it. You have to subtract two coordinates, two y coordinates and your two x coordinates, and it doesn't matter which one you start with. So I'm just going to pick this one. I'm going to start with that y coordinate, and I'm going to subtract from that this y coordinate. So whatever y coordinate I start with, I have to pick its partner in crime, -3. That goes directly below the 4 because they're partners. Okay, and so what goes directly below the -2 is a -4. So when I do this calculation, I get 6 over 1, so my slope is 6. I'd like you to do the next one at your seat, please. Okay, so what do we get for the slope here? -7/5. You can write it this way. You could write it this way. Or you could put the dash out in front of the whole darn thing. Doesn't matter where that dash goes as long as you got the dash. So you have 4, -2, which is here, -1/5, which is here. You connect them, so the first thing you say to yourself is, I better end up with a negative somewhere, or else I'm doing my arithmetic wrong. Okay, so my change in y is 5, take away a -2. I'm going to start there. And then the partner of 5 is -1, take away a 4. So that's 7 over -5. So I saw -3/5. So there was an error here with not writing -2. You just put 2. I'm trying to remember the other ones I saw. Well, that's the one I remember anyway. So you just got to be careful when your coordinate is actually a negative number and you're subtracting it, put it in parentheses so that you don't use the subtraction sign as the sign of the number. Okay, that's just a little thing that you can do to help organize how you write this. Okay, I think this is interesting that at this point this is pulled out. Notice this is pulled out of your book. And M, even though we haven't been told what M is how we represent slope. M represents slope. It's the letter that we use. And it's an interesting, if you're interested in historical notation for math or even some history of math, it's interesting to try to read why did we come up with M to use slope. And there's no definitive answer there. There's people that say it's because of this reason and people that say because of that reason. But it's an interesting thing if you like that kind of stuff. So M represents slope. And when a line rises as we move from left to right, we say the slope M is greater than 0. When it decreases, we say the slope is negative. When we have a horizontal line, we say that there's no slope. And when we have a vertical line, we say it's undefined, because then we'd be trying to define by 0 because there's no change in our x value. So which of these graphs above does not represent a function? The what? Farthest to the right. Yep, the undefined slope, the vertical line, right? So this is not a function. So because if you did the vertical line test and you went down through that, you'd hit a lot more than 1 point, right? So every time we talk in this class, and any other class for that matter, about linear functions, we are always talking about non-vertical lines. Non-vertical lines. Okay, so linear functions are non-vertical lines. They can be horizontal, they can rise left to right, or they could fall from left to right. They could never be vertical lines. So let's take a look at the first form of a line. We're going to look at several different forms of a line today, how to write several different forms. Now, you all have your favorite, and I know what it is. And students say, but do I have to do the other one? Yeah, you got to see it, because number one, when we move on to things like quadratic functions and exponential functions, the idea used to find or to write the equation of a line other than the chorus effect, chorus, y equals mx plus b, which is what everybody says, okay? It will help you if you see this other form. So we're going to start there today, the point slope form. So somewhere in this form you should see a point, and somewhere in this form you should see a slope. So how to arrive at that? So who just yawned? Cornelius? Oh, okay. Go ahead, Cameron. Just,
Remember that a line always has the same slope, no matter which you calculate it. Actually, my points x1, y1, x5, we'll still get the same.
right. So, and again, how do we calculate the slope? The slope is a change between any two y values, and we're used to seeing y2 take away y1 and x2 take away x1 because we're looking at two fixed points. So if we just said we're looking at 1 point, this equation is solved for the slope. That's the language we use. It's solved for the slope because m is all by itself, right? I now want to solve this equation for the numerator. So I want an equation, the same equation, an equivalent equation. So that's why I can use my double arrow here. I want an equation that's solved for the numerator. So that means I got to get rid of the denominator. I know how to do that because I've learned that when I have a rational equation, I can multiply both sides by the LCM, which is just x take away x1. Here's my foo-foo. This cancels with that. So I get y minus y1 on the left side equals the slope times x minus x1. So this is what we call the point slope form of a line. And I think it might be clear why it's called the point slope form, because you have the slope right there, and you have the coordinates for 1 point, one of your points on your line, and it's used that the coordinates from that 1 point is used in this equation. So this is called the point slope form. Okay. So let's take a look at a problem where we come up with the equation of a line using the point slope form. So the first one, you're already given the slope, so you know this is what m is equal to. Here's your point, so x1 is 2 and y1 is negative 5. So it's just a question of substituting it back in to the equation we just looked at. And again, students like, oh, this is like a whole new equation. No, it isn't. It's just the slope equation. If you take this factor right here, x minus x1, you divide both sides by it, you're back to your slope formula. Okay? The difference is, instead of 2 points, you're keeping these as arbitrary or generic points. So you have an equation. All right, so where you see m, you're going to replace m with 6. And where you see y1, and this is the only mistake I see students make. And this happens a lot, and I think because you rush and you want to do something else other than your math homework, right? The first coordinate you see here is the x coordinate, right? But what's the first coordinate in your formula? A y1, right? So often students aren't thinking, and they just take this 2, and they just kind of real quick, they take the 2 and they put it right there in the first slot. But it's the y coordinate that goes here. So it's y take away a -5 equals 6 times x minus your x1 coordinate. So you can simplify this to be like this. And now this is, you're done. That is the equation for a line that goes through the point 2, -5 and has a slope of 6. You don't have to do anything beyond that. If I ask you to put something in point slope form, this is what the answer should look like. Or you could even keep it like that. Either version, either one, either or is fine. Okay. So what's the problem with my second question? I want to write an equation in point slope form that passes through the points -2, -1, and -1, -6. What's my problem? Why can't I do it as quickly as this one right here? I need to find the slope first. So now I need both of these points. So I'm going to write in x1, y1, and x2, y2, just so I don't get lost in my subtraction. So I do the change in my y over the change in my x. So y2 is -6, and I'm going to subtract from that y1. x2, its partner, is also -1, and I'm going to subtract from that a -2, which is x1. So there's a change in my y over the change in my x, and I get a -5 on top and a +1 on bottom, so that means my slope is -5. Now I go to my point slope form, which looks a lot like my regular slope, except I've put the change in x right beside my slope. Okay, I know my slope, and I know 2 points. So now you just pick whatever point's your favorite to put down here in this formula. Does anybody have a particular favorite point here they want to use? Would someone choose one even if you don't have a favorite one? Well, that's not a point. -2, -1. Okay, thank you. All right, so we've got y take away -1 equals -5 times x take away a -2. So in point slope form, this is all I have to do, and I am done. Boom. That's it. Okay. So, in fact, I'm going to take this other one out here because I want to show you the advantage that you have when it's in this form, even if you don't believe it. So, when you leave something in this form, in your point slope form, you can go right to your graph and you can graph a point. You know 2, -5 live on that line. Here you know -2 and -1 live on that line, because remember, your point slope form is written with subtraction. So if you have a plus here, you must have been subtracting a -1. So you know your y value is -1 and your x value is -2. So you got a point on your graph, and then you can use your slope to walk to any other point on your graph. So looking at that equation, you should be able to tell, and this sounds like a really good question I could ask on a quiz sometime. So if I gave you, let's practice right now. If I gave you this and asked you what point is on that line just from looking at that equation, can you tell me? Okay, remember we have our x coordinate first and our y coordinate second. Want to try again? 2, -3, right, okay. 2, and if we put this as subtraction, it would have to look like that, because that's how the original formula was before I simplified it. So y1 was a -3, and x1 was a +2, okay? So that's the little variations that teachers can do on information that makes it a little unfamiliar, but you have enough in your background with a little thinking to answer. Okay, so now we're going to look at the slope-intercept form. And what most people don't realize is that the slope-intercept form actually can be derived from the point-slope form. Because with the point slope form, we want to now use that particular point. There's your y-intercept. All y-intercepts have x is 0, and then the value is something, and we're choosing the letter b. So if we take our point, before we write it in here, let's show how we derive it. So if we take our point slope form, and we now substitute this point into the x1, y1 spot, well, y is b, y1 is b, my slope is my slope, and x1 is 0. So this leads us to y minus b equals m times x. X take away 0 is x. And then when I solve this for y, I get mx plus b. And that's the form of a line most of you are very familiar with. It's called the slope-intercept, because the slope is always where it is. It's the coefficient of your x variable. And b represents this point, 0, comma b, which is your y-intercept, or whatever you're graphing on your vertical axis, whatever that variable happens to be. Okay. So let's take a look at this. So when I look at, just like with the point slope, when I look at a function, a linear function, this is called a linear function. Okay. And here y equals f of x. When I look at a linear function in the slope-intercept form, I know exactly where to go to make a point on my graph. Where do I go? What's the first point I can graph right away, just looking at the equation? 0, 1, my y-intercept, right? Okay. And then from here, I use my recipe. My recipe tells me how I can move from that point to another point, and I follow this recipe. It's called my slope. God bless you. Okay. And I can use either one of these because both of those are equal to positive 3/5. So let's suppose I use 3 divided by 5. So the change in my height is 3. So that tells me I can walk up 3. And then I can walk to the right 5. 1, 2, 3, 4, 5. Boom. I've got a second point on my line. And most people are confident enough that they could draw a line. I like to graph 3 points so that if they all line up, then I feel a lot more confident. So since I can't go up 3 anymore because I've run out of space, I'm going to use this recipe. I'm going to move down the line. So I'm going to go down 3, 1, 2, 3, and then this negative 5 says I move 5 to the left. 1, 2, 3, 4, 5, and there's my other point on the line. So now I feel really confident because those 3 points are all collinear. They're all lined up. Whoops. Okay, I have trouble drawing straight lines on this. Here we go. It's better to almost do it freehand. Okay, so let me get that out of there. So you put an arrow on either end because this extends to infinity. And this is something, put a little star on your paper. Whenever you graph anything in this class, you always label whatever the graph is with its equation. So f of x equals 3/5 x plus 1. So if you're handing in a project, okay, if you're handing in a project and you're graphing a line or you're graphing a parabola or something else later on called a polynomial function or a quartic, you'll always label the graph with the appropriate equation. That's just like putting a title on a graph, which you're always supposed to put a title. Because when I see this equation here, I know that this graph represents the entire solution set. That's what it does. Every point on that line is a solution to that equation, that function. Right? So put a little star here if you're not used to doing that, just as a little reminder. Okay, so if you recall, this should look familiar, I hope. Does anybody recognize this? It wasn't too far in the near past. What? Yeah, this was from Piecewise on Wednesday, right? No one peek at the pink sheet now. Now, on Wednesday, I gave you the actual equations for all the pieces. How many pieces did we have here? 3, right, 3. So we had the situation where the pool was filling up, and that was between 0 hours and 20 hours, right? And then we had another piece where we were between 20 and 30 hours. And then finally, the drain was, the pool was draining between 30 and 50 hours. Now on Wednesday, I gave you the equations to put in here, okay? Today, now that you know about straight lines, I'm going to ask you to fill this in, but we're going to take not as long as having you do all three. So I want tables 1 and 2, to come up with the equation for this line right here, that line segment, and put it over here. Because now that you know how to do this, you'll no longer be given the pieces for a piecewise. You're going to have to be able to look at the graph and figure it out. Okay, I'd like tables 5 and 4 to come up with this one. Tables 5 and 4 to do this one, the red line segment where the pool is draining, and I'd like the middle table to come up with this one, table 3. Okay, and so when each table is done, if it's more than one table, confer, and if you agree, one representative can come up and fill in each of the slots here. Table 3 only has to agree with itself. Okay. So regardless of which table you were at, you will be responsible to be filling out all 3 of them at some point on a quiz or a test along the way, or for homework. So make sure you've got the answers. You have them on the pink sheet from lecture 13 as well as on here. So if you made a mistake for whatever one you were responsible for, like if you didn't come up with 3/10 x plus 2, make a little note to yourself, Shane, to do this one, okay? And check it with Linda on Monday, okay? So if you had any problems at all, make sure, because this would be what I would consider like minimal prerequisites for this point on, is how to come up with the equation for a line. And if you're having difficulty with that, then we definitely need to work more problems. I can create some problems for you and give them to you, but you have to come see me outside of class, all right? So horizontal and vertical lines, and these have special equations. I don't usually memorize. I really don't. As many years as I've been teaching mathematics, I don't remember which one is like y equals, is it the y equals the b or the x equals the a? I don't even do that. All I do is I picture a horizontal line in my head, like this one. And I think about coordinates on that line. I just put a few coordinates in my head. Of course, the first one I see here is 0, 3, right? The y-intercept. And then I notice that anything along this line, what coordinate along this horizontal line would be the same as 0, 3? Which of the coordinates would be the same as I move left and right? All of them would be the same? What would be the same about all of them? Huh? The y, right. They're all exactly the same height above the x-axis. It doesn't matter where you are on the x-axis. Everything is going to be 3 steps up from the x-axis, right? Every point here, 4, 3 here, no matter where I go. Okay? Remember, we gave a special letter to that y-intercept, right? Back with the slope-intercept form. What letter did we give that intercept? B. So when we write the equation for a horizontal line, we say it's always going to be y equals a constant. They use the letter B, okay? Now, there's no x's in there, because whatever x is, it doesn't matter, because every single y is 3, and that's the end of the story. So horizontal and vertical lines should really be your friends, but it does cause people like issues, right? Same thing is true with vertical lines. If I ask you to find this equation, I always just start with where the vertical line intercepts my x-axis, because I'm really used to finding x-intercepts, and over here I was used to finding y-intercepts. And then I just think really quickly in my mind about 2 other points on there. And I say, okay, what do all these points on this line have in common no matter where I go? What do they all have in common? Say it. What is it? What is it that they have in common? X is what? If you can say it, you can write it. X is -3. Guess what? That's your equation. So in general, we say X equals A. Okay, so the equations for a vertical and horizontal line are always constant, always are represented by a constant number. There's no variable term in there at all. All right. All right, so in general, the last form of a line we have looks something like this. Here's a typical last form. This has this form right, almost has that form. Here, let me put it like this. This is called the general form of a line, okay? This is called the general form. We often work with this form where you might be working with a situation where you know, like you have two different types of coffee, for example, and well, coffee's a lot more expensive now. What would be $3 a pound? And maybe like organic bananas versus, you know, generic market bananas. This is $3 a pound, and this is how many pounds I buy. $2 a pound, and this is how many I buy, and I pay $12. And you'd want to try to figure out how many pounds of each type of banana you bought. Well, you'd need to have some other information because this is just one equation. This is just one equation with two unknowns. So you could graph this and you'd have lots of possibilities. So if I told you I bought twice as much of one type of banana as another, then you could solve it. You'd have another relationship to use. But the general form is where you smush everything all over one side of the equation, just like you do for what kind of equations? Quadratics. And notice we use A, B, and C again. Okay? But this time you have two variables. Okay, when you look at a general quadratic, not a function, it's ax squared plus bx plus c. And we often use the letters at the beginning of the alphabet to represent constant values, and the letters at the end, the x, y, z's, the w's, to represent your variables. That's just a little like standard math notation. So let's take a look at this. Here is a graph in general form, okay? So if you were going to graph this, right now you look at this and you say, yuck, I don't get any information from looking at that. You don't see your y coordinate right away, your y-intercept, I mean. You can't see a point on the line like you can with the point slope. You say, this is garbage, right? Well, so you want to change it. So let's change it to point slope form. Okay, the point slope form. Well, how would you do that? Changing it to the point slope. That would be hard to do. Okay, you want to reduce it? Okay. Divide everything on both sides by 3. Oops. Okay. All right. But point slope, I don't know. Let's see. Point slope says y minus y1 equals the slope times x minus x1. Yeah, I don't know. I don't know if I like point slope here. Do you? How about if I did this? Would it be a little bit better if I said this? Yeah, slope intercept would be a lot better because the slope intercept form is solved for y. I can solve this thing for y. I don't know how I solve it for y minus y1 and x minus x1. So it's a typo. Okay, so whether you already did what Adam suggested, which is to divide everything through by 3, you're going to divide everything through by 3 in the end anyway, at least 3. So let's start over here with our first equation. If I put it in slope-intercept form, you want to isolate y. So you're going to move everything else out of its way. You're going to subtract 3x from both sides, and you're going to add 12 to both sides. So I get 6y equals negative 3x plus 12. Is everybody with me now? Okay. And now I want 1y, so I divide everything through by 6 on both sides. I get y equals negative 1/2 x plus 2. Now I can go right down to my graph. I know a point. I know my y-intercept is 2. I go there. I know my slope is negative 1 divided by 2, or 1 divided by negative 2. And I use that recipe to get another point. So I'm going to go down 1 and to the right 2 and get a point. Down 1 and to the right 2. And that's all I need to make my line. Voila. We're done. No, 3 divided by 6 is 1/2. It's a fraction 1/2. Okay. All right. Now let me tell you, folks, the general method when you have a line in general form like this is not to convert it to any of these forms to graph. What you do is you put it 3x plus 6y and you put your constant on the right side, and then you use your intercepts because it's like this when you do your intercepts. So if you found your x-intercept has y equals 0. So you find your x-intercept first. You want to find the value of x when y is 0. So you go, oh, 3x equals 12, x equals 4. So you're done. You've got 4, 0. Boom, just like that, 4, 0. So when your line's in the general form, put your constant on the right-hand side, and then find both intercepts. So now it's the y-intercept turn. And when I'm doing a y-intercept, I know my x is 0, and I'm trying to find my y. So I erase this, and I say, okay, now it's y's turn. So x is 0. Now I figure out what y is. The minute x is 0, that's gone, so y is 2. And there's your intercept, and boom, look how quick that was, right? So these are the little things you want to write in your notes, right? Either on your lecture notes. Woohoo, look at that. That was cool how that happened, right? These are the little things you want to write. You want to say, if I have a line in general form, to graph it, the XY intercept method, it's called the intercept method, is really quick. You can do it just like that. Versus having to change it, because what if, Shane, right? What if in changing it to this form you made a little mistake? The whole thing's screwed up, right? Yeah. So it's better to try to make as few changes as possible, but know another method. Okay. So this is like maybe 3 or 4 classes of 106 reviewed in like 35 minutes, 40 minutes. Okay. So this is just a summary of what we went over today. And here is a great exercise called the fraying knot. And if you're a young man, you may want to see if you're in this age. Anybody in here 25 to 29? No? Nobody in here 25 to 29? Okay. Anyway, so it's an interesting story about what's happening today with people choosing to get married or not to get married. So you can work through this. You've got 15 full minutes, so you should make great headway, Ricky. Right down the line. Okay. Interesting.